In the present video, we will discuss the applications of steady flow energy equation. First application is nozzle and diffuser. Nozzle is a device that increases the velocity of a fluid by reducing its pressure. Similarly, diffuser is a device which increases the pressure of a fluid by reducing its velocity. So here in the figure shows an insulated nozzle where heat transfer with the surroundings is negligible. We know the steady flow energy equation, that is H1 plus V1 square by 2 plus GZ1 plus dQ by dm equal to H2 plus V2 square by 2 plus GZ2 plus dW by dm. So here given the insulated nozzle, then heat transfer with the surroundings is negligible, then dQ by dm equal to the 0. And in the nozzle, there is no shaft work, so dW by dm also 0. And moreover, change in potential energy is also 0 because elevations at the entry and exit are the same with respect to the datum. Then we are considering there is no change in potential energy. Then steady flow energy equation will become so here there is no heat transfer, then dQ by dm equal to the 0. No shaft work output, then dW by dm also 0. And negligible potential energy, then G into Z2 minus Z1 also 0. Then steady flow energy equation will become H1 plus V1 square by 2 equal to H2 plus V2 square by 2. Let's consider this is the equation 1. And we know the continuity equation which gives the M equal to A1 V1 by nu 1 equal to A2 V2 by nu 2. Here A1 A2 is the cross-sectional area of the nozzle and V1 V2 are the velocity of the nozzle at the entry and exit point. Similarly, nu1 and nu2 is the specific volume. Let's consider this is the equation number 2. So then, when the inlet velocity or the velocity of approach V1 is small compared to the exit velocity V2. So here V1 we have to consider the negligible. Then steady flow energy equation will become the H1 equal to H2 plus V2 square by 2. This equation we can be rewrite as the V2 equal to root of 2 into H2 minus H1. So this is the steady flow energy equation for the nozzle. Similarly, equation 1 and 2 are also applicable to a diffuser. Let's see the second application, throttling device. When a fluid flow through a narrow or restricted passage, such a partially opened valve, orifice or porous plug, its pressure decreases significantly. This process is called a throttling process. For example, fluid flowing through a partially opened valve in an insulated pipe is a throttling process. In the figure, it shows the schematic representation of the partially opened valve. It is the throttling process. We know the steady flow energy equation. In the throttling device, it is the insulated. So dQ by dm equal to the 0. Moreover, there is the no shaft work output. So dW by dm also 0. And also here observe. So elevations at the entry and exit points are the same. So there is no change in potential energy. So here there is the no heat transfer, dQ by dm equal to the 0 and no work output, dW by dm also 0, and moreover there is no change in potential energy. Then steady flow energy equation will become the H1 plus V1 square by 2 equal to H2 plus V2 square by 2. Moreover, In the throttling device, fluid velocity is very low, so the kinetic energy terms can also be negligible. So here there is the no kinetic energy. Change in kinetic energy also 0. Then steady flow energy equation will become the H1 equal to H2. The enthalpy of the fluid before throttling is equal to the enthalpy of the fluid after throttling. Next application is turbine and compressor. The turbine's main purpose is to extract energy from the fluid and convert it into shaft work. Fluid enters the turbine with some velocity. Then inside the turbine, its pressure or enthalpy energy is converted into shaft work. At the outlet, the remaining velocity may be comparatively very small. Therefore, the change in kinetic energy is often small compared with the shaft work. Turbines and engines produce power, while compressor and pumps need power input. In a well-insulated turbine, as shown in the figure, fluid velocity is usually small, therefore kinetic energy terms can be neglected. So moreover, we have to neglect the change in potential energy because the difference in height between the inlet and outlet is usually very small. So in the turbine, we have to considering the dq by dm equal to the 0 because it is the insulated, there is the no change in heat transfer, and kinetic energy and potential energy also we are considering the 0. And we know the steady flow energy equation, and here dq by dm equal to the 0 and change in kinetic energy and potential energy also 0. Then steady flow energy equation will become the H1 equal to the H2 plus dW by dm. And this equation we can be rewrite as the H1 minus H2 equal to dW by dm. It's seen that the work is done by the fluid at the expense of its enthalpy. Similarly, for an adiabatic pump or compressor, work is done upon the fluid and W work done is the negative. So in the compressor, steady flow energy equation will become the H1 equal to H2 minus dW by dm. So dW by dm equal to the H2 minus H1 in the case of the compressor. Next application is the condenser or heat exchanger. A heat exchanger is a device that transfers heat from one fluid to another. In the figure, a steam condenser is shown. Here I have to observe steam flows outside of the tube and cooling water flows inside the tubes. So heat will be transferred from steam to the cooling water, causing the steam to condense into the water. So in this case, the kinetic energy and potential energies changes are neglected. Moreover, in the case of the condenser or heat exchanger, there is no external work done, and also there is heat transferred only between the tube fluids inside the heat exchanger. So in the case of the condenser or heat exchanger, we are considering the Q equal to the 0 because it is the insulated one and heat transfer is taking place between the tube fluids only, and work done also 0 because there is no shaft work output, and kinetic energy and potential energy are the neglected, we are considering the 0. So steady flow energy equation in this case is ms h1 plus mw h3 equal to ms h2 plus mw h4, where Ms and Nw are the mass transfer rate of the steam and water. So Ms is the mass transfer of the steam, Mw is the mass transfer of the water, and H1 is the enthalpy of water at the inlet position, and H3 is the enthalpy of the steam at the inlet, and H2 is the enthalpy of the steam at the outlet, and H4 is the enthalpy of the water at outlet. So this steady flow energy equation we can be rewrite as Ms into H1 minus H2 equal to Mw into H4 minus H3. So these are the applications of the steady flow energy equation, and thank you.